All right, so now we're going to look at the diffusion coefficient or diffusivity, and specifically look at self-diffusivity. So when we refer to self-diffusivity, and again, that's the term D in Fick's first law. And if we talk about of an atom or other species, so ion, it's a measure of the ease and frequency with which that species jumps around in the crystal. And that's in the absence of external forces. So here we're talking about the random hopping of atoms or ions in the crystal lattice and the ease and frequency in which it does jump around in that lattice, and it's in the absence of external forces. So that's concentration gradient, electric potential, and things like that. So we're just talking about completely random. So this motion is completely random hopping. And it's induced by thermal energy. So we have enough energy in the system because we're always above 0K, and so there's always vibrational thermal energy that goes to the atoms, and that allows for it to move through that gap in atoms to go into a vacancy or interstitial, etc. So since it is a thermally activated process, then we can write it as like we write all other thermally activated processes, which is the diffusion coefficient D is equal to a pre-exponential D naught, or D0, times an exponential, and inside the exponential is an activation energy or barrier, Q, divided by KT. So again, you've probably seen this KT term come up in a number of expressions, and we're going to get to this in a bit, where this comes from. So Q is the activation energy. So it's not a function of temperature. We have D naught, which is a weakly dependent on temperature. But usually assumed independent. Kind of for a first approximation, we assume it's independent. And so diffusivity, D, depends critically, spell that again, on the stoichiometry and purity of a ceramic. All right, so now let's get to how we actually measure this, right? It depends on stoichiometry and purity, and we know it follows this general, this is an empirical equation as well. We know it follows this relationship, but let's talk about how we actually measure diffusivity. So let's get on to the next page here. So measuring diffusivity. All right. So again, we're talking about self-diffusivity at the moment. And so there's no concentration gradient. Concentration, I'm just abbreviating here. Gradient to measure, right? So measuring a concentration gradient is fairly easy, right? If we have a method for measuring concentration or atoms and so forth, we can do that. However, we're not doing that in this case because we're talking about the same atom or ion, self, right? And so it can't be used to measure self-diffusivity. Okay, but let's look at, let's take a look at self-diffusion. So let's just say I want to look at self-diffusion of manganese, so that'd be a manganese ion in manganese oxide, right? So that would technically be manganese 2+. So what we can do to measure self-diffusion is actually to introduce a portion of manganese atoms that are radioactive isotopes. So they're specific isotopes of manganese that are radioactive. And they're obviously isotopes, so they have a slightly different mass because it has a different number of neutrons. However, these differences are slight. So there's very slight variations in mass. But what we do is, for at least for the first approximation, if we assume these isotopes are close enough to manganese. And so at this point, what we do is then we look at the diffusion of these isotopes. And we can do that by radioactive measurements. So those are measurements that are easy enough to make, and we're able to see differences and thus determine how far and how fast they move. So moved in the Mn solid. So the idea here is that we can use radioactivity, and we're kind of assuming that there is a slight difference in mass, but it's small enough that we can basically consider manganese, radioactive or regular, as the same, but the radioactive portion allows us to see where those radioactive portions are within the solid. And so it gives us a marker, effectively, to measure that atom and ion, and then we can track it and we can measure diffusivity or self-diffusivity in that way. So that's how we kind of go about measuring diffusivity when we're talking about self-diffusivity.